Okay, so we've talked about all of these concepts so far. In particular, the thing that we're going to be using going forward is really going to be the current and the voltage. That's going to be our bread and butter when it comes to electrodynamics. There is a lot of use in Coulomb's law as the foundation for all of this stuff, and especially when it comes to things like converting between mechanical energy and electrical energy. But the biggest bang for our buck is going to be this current and voltage. So how are these two things going to be related? Good question. There is another law of physics, Ohm's law, that relates current and voltage. This relationship is going to be voltage is equal to current times R. This R. This is resistance. Resistance is the impedance of charge being able to flow. And we're going to need to be able to calculate this for different substances. So the way we can think about this is that current is inversely proportional to resistance. So the bigger resistance is, the lower current is going to be. The lower resistance is, the more current will be. Now what we're really saying here is, if I've got a charge, let's just give ourselves a little point charge here, and it's got a certain voltage behind it. We're just going to draw these lines to make it look like something's pushing this. That would be our voltage. It's almost like this is trying to push this charge along, and it wants to move. It's going to move according to that current. How much of that charge can move through at a time is going to be fully dependent on the resistance of this space. Now, it's convenient to think about charges in this way, but charges don't behave like just these little points of mass that we could look at. You know, it's like when we looked at conservation of energy. We could look at a ball rolling down a hill. Now that ball it might as well be a dot. It's convenient to think about charge as being the same way, but charge can be more of an abstract concept as well. I can have an entire plate of charge moving together. And I can have something as small as an electron carrying charge. So resistance is really going to be impeding that charge. It's not a physical thing, it is an electrical thing. But it is a native quality within different materials. So how do we calculate resistance? Well, resistance, let's think of it this way. The first thing is that resistance is going to be proportional to a concept called resistivity. Now that seems kind of arbitrary, it seems a little obvious, but resistivity is denoted by this Greek letter, rho. It looks like a lowercase p, but it is the Greek letter rho, R-H-O. Rho, great, R-H-O. So, resistivity is going to be the native property within a substance. For example, I've got a list here. Silver has a resistivity, rho value for silver is Ag, is, what was it, 1.59 e to the negative 8. So its resistivity is extremely low. What that means is that it's very easy for current to move through something like silver. It would be a conductor. Another example could be something like rubber. Rubber is actually a really good example. Rubber could have a resistivity anywhere from 1 to 100. Let's just round it out. 50. 50 E 13. So you see that difference? The difference in magnitude between these two? Resistivity is a native quality of a substance, and it is the most diverse quality of any substance. I mean, even density doesn't have this massive difference in orders of magnitude. There is nothing that is more variable through different materials. So if we look at rubber, 50 with 13 zeros after it, that is a massive number. It is extremely difficult for charge to flow through rubber. And that's why we call it an insulator. It insulates against electric current. So that's a concept that we need to keep in mind, is that depending on an object's resistivity will make it either a conductor or an insulator. So these charges aren't just floating through empty space, they're moving through something, through an object. Even lightning is traveling through air, and air would have a resistivity. And I don't have it on my list, I don't know it offhand, but it would have a certain value. And air is going to be a pretty good insulator. It's going to have a larger resistivity, which is why when lightning finally does strike, it transfers a massive amount of charge, because it has to have a massive amount built up to overcome that giant resistance. Okay? What else is resistance going to be based on? Okay, well, we've got it proportional to resistivity. Well, let's think of it this way. The most common time we see electricity flowing, we see charge flowing, is through something like a wire. So let's use that as our example. I'm going to draw it larger here just for exaggerated purposes. I've got a wire here, and let's use a copper wire. Copper is a classic material that is used in wiring because it has a very low resistivity. It makes it really easy for things to travel through it. And copper would have these little copper atoms all the way through this thing, and each one would have a little electron. Copper has one valence electron. So if I try to push a charge through this, let's say I've got charge in the form of an electron trying to push through this thing, it's going to have to push each of these electrons along. So how could I make this more difficult for that charge to move? In other words, how could I increase the resistance? Well, quite simply, if there was more along the line that it had to move, it'd be more difficult. Think of it like if I've got something like a heavy lead ball, and I try to move a row of heavy lead balls. The longer that row gets, the harder it is to move even one of them an inch. Or if I've only got a group of 3, it's very easy to move. Even something light like basketballs, if I tried to move just one, it's very easy. But if I've got a row of 200 basketballs, it suddenly becomes difficult to roll them all. It's going to be the same with the electric current. So if I've got a longer wire, my resistance is going to go up. So that means that resistance would be proportional to length. There we go. Okay, well, how can I change this? How can I make it easier for this to flow? Well, the way we can think of this is, just like this example, I've got a super thin wire that's only an atom thick. What if I made it 3 atoms thick? And instead went something like this. So I still have all these little atoms of copper, and they each still only have one electron that they can move on. But now when I try to add in even just this one bit of charge, it's able to push at all 3 at once. Now it's easier to move. So if I get a bigger area, then it's going to become easier for that charge to move through. Because remember, we're never going to be just looking at one little bit of charge. We're not going to be looking at just one electron. I would have a whole army of electrons sitting here trying to make their way through. It's less like a single electron moving and more like a crowd of people trying to rush into a Walmart on Black Friday. The bigger the doors, the more are going to get through. So in that same way, resistance is then going to be proportional to the inverse of area. So these are the three relationships that resistance is going to have. So if I put them all together, my resistance is going to be equal to rho times the length divided by area. Now, the resistivity of a substance, these have been tested and determined experimentally. It's one of those properties that's extremely difficult to precisely define just by knowing what a material is like. We can make generalizations like all metals are generally good conductors of electricity. Water that has salts dissolved in it would be a good conductor of electricity. But rubber, plastic, things like that, those are insulators. So we have general ideas about the resistivity of a substance, but to know its exact resistivity, it needs to be determined experimentally. And so we could do that, or we could just look things up in a table online. That's what we're going to do. So the document I'm going to share with you has 4 problems asking you to determine the resistance of a material based on its resistivity, its length, and its area. So I give you all of these pieces of information, or I'll just give you a material and I've got a table on the worksheet that has the resistivity on it. So go ahead, go through and calculate that. We'll add this equation to our belt along with Ohm's law, and after this we're going to be able to put everything back together. All right?